So here we are, nuclear chemistry. This is a rather exciting topic. We're not going to go like super duper in detail about it, but we're going to cover some key topics that relate to this branch of chemistry. Um, the concepts that we're going to cover, they're actually not super complicated, but that's not to give you the false impression that nuclear chemistry is easy. It's not. And your knowledge of chemistry, your knowledge of physics, your knowledge of math has to be on point. Because when dealing with nuclear um, species that are radioactive, if you are not aware and of how to deal with these molecules, you could actually injure yourself quite badly. But that being said, let's talk a little bit about nuclear chemistry and how the origins arose. You may have heard about the alchemists. The thing about the alchemists is that and this dates back to the 16th century and probably a little earlier than that. The whole idea was that this premise that came from some of the philosophies taught in old Greece, um, basically kind of gave people the idea that there was an elixir, a philosopher's stone in the ether being the air, something that permeated throughout. But there was a philosopher's stone that you could extract from this ether, which could be used to transmutate an element into another. And the whole premise was going to be that you could take these oxide salts that you could utilize to get a pure metal, such as mercury or tin or copper, metals that were not considered to be noble. And with this elixir of life that you could extract from the ether, you could convert the common metal into a noble metal like gold or silver, right? And of course, whoever found this particular elixir of life would have been like rich beyond belief. The thing is that such elixir of life doesn't actually exist. And so, not to say that they were wasting their time doing this, there was some chemistry that was learned along the way, and alchemy was the pave road into chemistry, or that led to chemistry. But this idea that you can transmutate elements, didn't really pan out for them. And when chemistry became a science and the scientific method became a thing, Dalton himself came up with some laws or some corollaries to experimental evidence that he had observed. The first one was that elements were made of indivisible parts, meaning that you couldn't break apart the elements any further than the element itself. All atoms of the same element have the same mass. Compounds are made of atoms of different elements. Okay, many molecules have atoms of different elements. Chemical reactions involve reorganization of atoms, and the last one is that atoms cannot be created or destroyed. Now, the funny thing is that this was kind of true, and this kind of destroyed alchemy, right? Once it was kind of established. But the truth of the matter is that these 3 points that I'm highlighting in red weren't exactly true and were kind of incorrect. And the reason why is because some of the things that happen in nuclear chemistry kind of break this notion apart. So we're going to look into these particular aspects, and we're going to see that the elements are in fact made out of other parts that are even smaller than the element itself. We're going to see that atoms of the same element can actually have different masses. We know those elements as being isotopes. And you could actually take an element and create yet a new one. So you could actually do the thing that alchemists were trying to do, but they did not know anything about nuclear chemistry to make that happen. And even if they did know that, they didn't have the equipment required to make that type of transformation happen. All right, so before we get into that, I do need to talk to you about nuclear symbols so that we can make sense of nuclear reactions. And the way we symbolize an atom, or specifically an isotope, is by using the symbol of the element in question. Down here on the left side, we have the atomic number of the element. This will be directly derived from the periodic table. Whatever element you're dealing with is going to have a very specific atomic number associated with it. And the atomic number, as well as the symbol of the element, are completely related to each other, right? what the other is. You cannot have different atomic numbers for one element. Whatever the element is dictates automatically the value of the atomic number. On the other hand, the value here, and the superscript value, is known as the mass number, and this number can actually change. And you can change it because you could have different number of neutrons present in an element that's creating different isotopes. And just to kind of remind you a little bit about this, the atomic number represents the number of protons, which in and of itself tells you which element you're dealing with. The number of neutrons is simply the subtraction of the mass number with the atomic number. And together, neutrons and protons represent the nucleus. And this is where all the nuclear reactions take place, hence the name of this branch of chemistry, nuclear chemistry. All right, so changes in the nucleus is ultimately what we're going to be looking at in this lecture series. Another thing that I also need to tell you about is relativity, because it is right at the nucleus that the processes of relativity actually take place. And it's kind of interesting because relativity, which is the theory that Einstein is best known for, is what explains the interactions, the intergalactic interactions of celestial bodies. And these are humongous in magnitude. And yet, the same equation that describes all of this, E equals mc squared, also dictates what happens with nuclear reactions. And as you'll see at the end of the lecture, I will make the connection between the very small and the very large as it pertains to relativity. The thing that I want to convey to you right now is that E stands for energy, m stands for mass, c is the speed of light, which you are squaring in this equation. And simply put, what the equation presented here by Einstein says is that energy is the same thing as mass. Mass is energy and energy is mass. And this has tremendous consequences in explaining how nature behaves and presents itself. All right, so to give you an idea, right, and to look at the units first of all, involving E equals mc squared, energy, if you calculate it the way it is in this equation, will give you values in joules per mole. That's if the mass is in kilograms. So you're going to actually have to change the mass to kilograms per mole. And so typically you could actually just use the atomic mass or the molecular mass of a compound in grams per mole. You change that to kilograms per mole, and upon multiplying that by the speed of light squared, you will get the energy in joules per mole. All right, so squaring the speed of light gives you units of meter squared over second squared. Kilogram times meter squared over second squared is what we call the joule. So that's how this works out altogether. And that's the reason why the mass needs to be changed to kilograms. So to give you an idea, if we look at carbon 12 reacting with one proton to give us carbon 13, if we look at the masses of these specific isotopes, we could actually see how much the mass changes going from the reactants to the products. We have a mass of 13.0033543838 grams per mole for carbon 13, 12 point, bunch of zeros grams per mole for carbon 12, 1.007, oh, that's our James Bond isotope, right? 1.007825.032. If we add the masses, the isotopic masses of carbon 12 and hydrogen 1 together, and subtract them from the isotopic mass of carbon 13, you find out that there is a mass difference of 0.004470194 grams per mole. And you might say, well, that's very small, that's kind of insignificant. But the point is that in the past we've stated that energy and mass, more importantly related to this, mass is neither created nor destroyed. So how could you end up with less mass than you started with? Where did that mass go? Well, this is where Einstein comes in. He tells us that the mass discrepancy that you have upon making carbon 13 from carbon 12 and a proton is ultimately turned into energy. So if you plug in this mass discrepancy into here, change the grams per mole to kilograms, so divide by 1,000, and multiply by the speed of light square, you're going to find out that you have basically turned that 0.00447 gram per mole of mass that you lost into ultimately 4.02 times 10 to the 11 joules per mole, or if you divide this by 1,000, the same thing as 4.02 times 10 to the 8 kilojoules per mole. This is humongous. This is in the order of terajoules worth of energy. So changing a little bit of mass into energy provides you with a lot of energy. And this is what happens in nuclear reactions. And also, this is the reason why when dealing with nuclear radioactive isotopes, you have to be very careful, because the amount of energy that gets generated upon a nuclear reaction can be so high in energy that exposure to it can mess up your own cells, your own DNA, your own, your own body. In the worst case scenario, if you get exposed to enough of it, your cells will undergo necrosis and you will die from the inside out. So, not to scare you or anything, but it is to be taken, with respect. All right, so this is how we'll use Einstein's equation. Just make sure to change your grams per mole to kilograms per mole, so that you end up with joules per mole upon carrying out the E equals mc squared calculation. And at the end, if I do ask you for it, don't forget to change this to kilojoules per mole. And also, to give you a perspective, this is also the same thing as 401.7 gigajoules per mole of energy. And if you recall your, Back to the Future, 1.21 gigawatts of energy was humongous, so much that Dr. Brown went running out of his house, cursing, cursing at life. So 401.7 gigajoules is a lot of energy. All right. So this thing that I'm gonna call the binding energy, we're also gonna refer to that in regards to just seeing how much energy it takes to make an atom or a specific isotope from the individual protons and the individual neutrons. And you basically do exactly what I did right here, and at the end you end up finding out how much energy gets generated from forming some atoms. And once again, we're gonna come back to this same idea towards the end of the lecture. One more thing that I want to show you. Okay, so this is the Los Alamos National Lab where I used to work in the past. This is located in northwestern New Mexico, about 40 miles from Santa Fe, the capital of New Mexico. And it's in this lab that the Manhattan Project took place back in the 30s. And for those of you that don't know, the Manhattan Project was the project ultimately that led to formation, or actually the development of the atomic bomb. So this was a result of, the fact that Nazi Germany was beginning to rise in power, and many nations were already scared of what, the Nazis were going to do. So the Manhattan Project came as a means to maybe not only outsmarting the Axis powers during World War II, but also to make sure that they weren't going to be annihilated, because they knew that, Hitler was not good news for anybody. So they developed the atomic bomb out of the ideas of Einstein. And what you can see here is a picture of one of the early scientists playing with a plutonium core, which is known as the demon core. And basically, he's just closing the demon core with a capsule, hollow capsule of beryllium that basically um, helps get protons bounce back into the demon core, thus yielding your nuclear reaction. And over here, of course, you see a nuclear reactor that nowadays we can use to power up cities, create nuclear isotopes used for medicine, etc., etc. So, it's not all bad, right? But the atomic bomb clearly is a highly devastating and highly damaging um, arsenal, right? So you don't really want to use it all that often, if at all. Okay, so let's stop the video right here, and in the next video we're going to start talking about the stability of nuclear species, and we're going to start talking about nuclear particles.